Good morning. My name is Frank Madrid, a computer science and mathematics senior at California State University, Bakersfield, and I will be presenting my group's PIC math research project on boundary point detection from tomographic data. Within the field of medicine, a fundamental problem has been to reconstruct the surface of a volume from a given set of randomized sample points, located both on and possibly within the volume itself. An accurate representation of the surface of a volume within the human body, such as a malignant tumor, can be used to properly diagnose and treat the patient. The specific surface reconstruction problem we considered was proposed by Dr. Derek Kane of Decker Research and Development. Dr. Kane posed the following question. Given tomographic data of a region surrounding a tumor, can we extract the volume occupied by the tumor? More specifically, how can we determine the surface enclosed in the volume, assuming the points are equally likely to occur anywhere within the volume itself? In addition, due to the decrease in strength of the sampling beam as the sampling beam enters the volume, do our proposed methodologies change when we are more likely to detect elements of the volume which are closer to the surface? Within this project, we implement a modification of the border algorithm, and we also ascertain whether implementing the robust Cocoon algorithm can allow us to further detect the sample points, allow us to further detect the boundary points of the sample. Implemented within the reverse k nearest neighbors algorithm, the k nearest neighbors allows us to determine the k closest points to any particular point within the sample. For example, within the figure here, the points P3 and P4 are the two closest neighbors to the point P1. The reverse k nearest neighbors algorithm assigns an r, k, and n value to each point within the sample. This value is determined by the number of times each point appears within the k nearest neighbors lists of the other points within the sample. As shown by the example, the points P4 is one of the two closest nearest neighbors to the points P1, P3, and P6. In border, Zia et al. Proposed border points of the sample will have relatively low RK and N values, while conversely, points within the volume will have relatively high RK and N values within a uniformly dense sample space, however. Within our implementation, we propose that border points will have relatively high RK and N values, while points within the volume, due to the decrease of the strength of the sampling beam, will occur far less, will have RK and N values which are relatively small. Within the example, boundary points depicted in red, points depicted in red have relatively high RK and N values, or an RK and N value greater than or equal to a particular value of alpha, a threshold, while the points depicted in black have a RK and N value lower than this particular value. Amenta et al. Proposed a construction, a surface mesh, from a sample set of points approximated via the medial axis of the sample points, known as the power cross method, or construction. The medial axis transformation is approximated by a subset of the Voronoi vertices which lie near the medial axis. Implemented within our project, the robust Cocoon algorithm serves as an improvement to the power cross construction by allowing the sample space to contain noisy data. As an example of this construction, consider a simple closed curve, a simple closed two-dimensional curve. Consider a subset of points used to approximate the curve. The power cross construction first constructs the Voronoi diagram, which consists of a sequence of Voronoi cells, where each cell is characterized by the minimized Euclidean distance to any particular point within the sample. Any intersection of three or more of these Voronoi cells is known as a Voronoi vertex. If you were to consider the Delaunay triangulation of the union of the set of sample points and the Voronoi vertices, if we consider the triangular edges connecting any two original sample points, we arrive at our approximation of the original surface by the surface mesh. Within our project, we implemented the reverse k nearest neighbors algorithm to ascertain which points within the volume, within the sample, have a relatively high RKN value. We propose that points with a high RKN value will be the border points of our original sample set. We first implemented the k nearest neighbor algorithm, and then we determine how many times each point appears within the k nearest neighbor list to determine the RKN value of the points. Further refining our boundary points, we then pass the results from our first method to the second method and implementing the robust Cocoon algorithm. Within our project, we consider tomographic data of a region surrounding three objects: a sphere, a right medial geniculate, and a suprachiasmatic nucleus. The sphere was generated by uniformly sampling the surface points of the sphere, while the geniculate and the nucleus were obtained from the Japanese Database Center for Life Sciences, suggested by Dr. Derek Kane. Within our experiment, we simulate noise by randomly perturbing a particular subset of the original sample data. The effect of this perturbation can be seen on the sphere, which consists of approximately 2,500 sample points with a level of 50% noise, and then again for 25% noise. We then show the effect of the perturbation on the geniculate, which is approximately 2,000 sample points for a 50% noise level, and then once again for the 25% noise level. Lastly, we show the effects of the noise on the suprachiasmatic nucleus, which has about 700 sample points for a 50% level of noise, and once again for the 25% level of noise. The goal of our experiment was to mitigate the effect of this noise on our original sample. After implementing the first method, we can see from the graph that implementing the reverse k nearest neighbor algorithm removed approximately 60% of the noisy points while preserving about 95% of the original sample points. This graph shows a relationship between the remaining noise and the remaining sample points. An emphasis was placed on our experiment to preserve at least 90% of the sample points while minimizing the amount of noise we maintain. The effects of our second method can be seen here, where the robust Cocoon algorithm successfully removed almost all of the noise from the sphere while maintaining almost all of the sample points, clearly showing the superiority of the robust Cocoon algorithm on the sphere data. When considering noisier data, the robust Cocoon algorithm still removes almost all of the noise while preserving approximately 85% of the sample points. However, the reverse k nearest neighbor algorithm maintains still approximately 95% of the sample points while removing on average 65% of the noise. Witnessing the effects of our experimentation on the right medial geniculate, again, the robust Cocoon algorithm has shown its propensity to remove most of the noise within our sample data. However, this time we're only maintaining 60% of the original sample points, while the reverse k nearest neighbor algorithm still is preserving approximately 95% of the sample points and removing consistently approximately 50% of the noise. Increasing the noise, we see similar effects for the robust Cocoon algorithm, as well as similar effects for the reverse k nearest neighbors algorithm. Lastly, we consider our experiment on the suprachiasmatic nucleus. The robust Cocoon algorithm still performed similarly by removing almost all of the noise and maintaining approximately 60% of the original sample points, while the reverse k nearest neighbors algorithm removed approximately, or remaining about 70% of the noise and still preserving almost all the data. And lastly, we see the effects of our experiment on the noisier version of the nucleus, where the robust Cocoon algorithm preserved about 20% of the original noise and about 55% of the original sample points, while the reverse k nearest neighbors algorithm preserved about 55% of the noise and still 95% of the original sample points. From this data, we can see that the reverse k-nearest neighbors algorithm is efficiently resilient to any changes of the sample size, as well as changes to noise, while the robust Cocone algorithm is particularly susceptible to changes in sample size, though it still efficiently removes most of the noise. In conclusion, we propose two methods to reduce the influence of noise on tomographic data. The first method implemented the reverse k-nearest neighbors algorithm, which was shown to be resilient to any changes in sample size and noise, while the second method, which implements the robust Cocone algorithm, is effective on sufficiently large data sets and has been shown to be less effective on small data sets. We would like to thank Dr. Derek Kane for proposing this interesting problem to us, as well as the MAA for the opportunity to present our research for the PIC math project. Thank you.